Alrighty, gang, welcome back. Sorry for the delay there. It's been a bit of a crazy morning. Some lovely individuals smacked into the back of my car this morning. I've been dealing with insurance assholes all day. And, well, you guys know how that stuff goes. It's no fun. But calculus is fun. So let's do some calculus. Turn on the screen share. To QQ. Come on. There we go. All right. So last time we got into this curve sketching stuff, we were able to sketch the graphs of a handful of functions by taking the first and second derivative to find where the function is increasing, decreasing, concave up, concave down, inflection points, mins, maxes, horizontal, asymptotes, x-intercepts, and all that good shit. Whew. The problems take a little while, right? They're not fast problems. I do want to go through at least one more of those with you guys today. The other thing we need to talk about is the mean value theorem, which is a really fantastic theoretical thing. It's not the most practical thing in the world for us at this level, but there are some fun, kind of surprising, and even a little bit relevant to my car crash story applications. So let's do it. This is MAC2311. Section number is 004, which is Calc 1. Yeah, close enough to know. Calc 1. And the date today is the 4th of March, 2022. Today we're going to do a bit more curve sketching. Which was section 4.5. And then we're going to walk backwards to the mean value theorem. Which I believe is section 4.3. The insurance asshole calling me. Oh, I hung up on them accidentally. All right, that's the right move anyway. So let's take a look in your textbook and grab ourselves a fun looking curve. All right, so we're curve sketching something. Ooh, that looks fun. Yeah, the inverse tangent of e to the x. That's not one that we have looked at so far. And that's the intent here is just to sketch, yeah. Two. I'll write it as inverse tangent like this. Right, of course, arctan and tan inverse, those mean the same thing. Neither of them have anything to do with the reciprocal or cotangent function. This is the function that is the inverse of the tangent function in the same sense that like the square root is the inverse of x squared. So remember the game here, we need to figure out where this thing is positive, negative, 0. We need to find out where the derivative is positive, negative, 0. Where the second derivative is positive, negative, 0. And we also want to identify any special symmetries or things like that. Okay. So the first thing we want to do, see where this function is 0, if ever. And then make a number line for this guy. So f of x equals 0. If and only if the inverse tangent of e to the x equals 0. This is us hunting for x-intercepts. And then the number line we would build here is what will tell us where f itself is positive or negative. So whether the graph is above or below the x-axis. you can solve this equation by taking the tangent of both sides. Right? Just like you can use inverse tangent to undo tangent, you can use tangent to undo inverse tangent. On the left-hand side, the tangent of the inverse tangent of e to the x is just e to the x. On the right-hand side, you have the tangent of 0, and the tangent of 0 is 0. So this gives us e to the x equals 0, but that's never true, right? This would be true if x was the natural log of 0, but this is undefined. Okay, so there are no x-intercepts. No x-intercepts. And if you test any particular point, the number line for f here is going to be somewhat boring. F is never capable of changing sign. This function is continuous everywhere because e to the x is continuous everywhere and arctan is continuous everywhere. So when you plug one into the other, the result is continuous everywhere. Because there are no x-intercepts, there's really only one region for f. It's negative infinity to infinity. And if you test, say, x equals 0, f of 0 is the inverse tangent of e to the 0, which is the inverse tangent of 1, which is pi over 4. In particular, positive. Okay, so the graph of this function is everywhere above the x-axis. Never touches the x-axis, never goes below the x-axis. Now we will do our first derivative work. So if we differentiate this guy, f prime of x, that means we're differentiating the inverse tangent of e to the x. So that would be 1 over 1 plus e to the x squared times the derivative of e to the x by the chain rule. All right, because the derivative of inverse tangent of u is 1 over 1 plus u squared. So this would be like your 1 over 1 plus u squared. And then you have to multiply by the derivative of the inside. The derivative of e to the x is e to the x. And if you take this guy, he's e to the x, then multiply by this fraction, you get e to the x over 1 plus e to the 2x. And we want to ask, where is this capable of changing sign? So where is this 0? Where is it undefined? Well, this is never going to be 0, right? Because the top is never 0. You can say f prime of x equals 0 if and only if e to the x over 1 plus e to the 2x equals 0. And multiplying both sides by that denominator, you get e to the x equals 0. And we just said this never happens. So f prime is never going to be 0. We could also ask, is f prime ever undefined? Right, because you can change sign there as well. Those are your critical numbers. That would mean the bottom is equal to 0. 1 plus e to the 2x equals 0, which would mean e to the 2x is negative 1. But this is also not ever going to happen, right? If you take the natural log on both sides, that's how you would solve this. You get 2x equals the natural log of negative 1. But again, the log piece here is undefined. Can't take the log of a negative number. So there are no critical numbers. The number line for f prime also looking a little boring. You can take any number, say x equals 0, to use as your test point in here. F prime of 0 is e to the 0 over 1 plus e to the 2 times 0 is also 0. So that's 1 over 1 plus 1, it's 1/2. In particular, it's positive. So f prime is positive everywhere, just like f. So my function's graph is always above the x-axis. That's what we learned up here. And my function is always increasing. That's what we learned here. Questions so far? All right, hopefully the second derivative will be more interesting. So if we calculate f double primed, oh, sorry, excuse me. All right, if we calculate f double primed, that means we're hunting for concavity and inflection points. F double prime will require the quotient rule. So here we can see f prime still. That's the bottom times the derivative of the top minus the top times the derivative of the bottom. So I'll write this out, 1 plus e to the 2x times the derivative of the top, e to the x primed, minus the top, which is e to the x times the derivative of the bottom. So that's 1 plus e to the 2x primed. And we have to divide this whole thing by 1 plus e to the 2x all squared. Low d high minus high d low over low low. 3 hours later, we get 1 plus e to the 2x times e to the x minus e to the x times. The derivative here requires the chain rule. Of course, the 1 will differentiate to 0, but e to the 2x, that's a chain rule derivative. The inner function is 2x. So we're going to get e to the 2x times the derivative of 2x, which is 2. And all of this still divided by 1 plus e to the 2x quantity squared. All right, we got some algebra to do. Distributing the e to the x here, we get e to the x plus e to the 2x times e to the 1x is e to the 3x. Minus, I'll put the 2 out front, this 2 right here. And then e to the x times e to the 2x is again e to the 3x. All over that same denominator. Combining like terms, I have e to the x plus e to the 3x minus 2e to the 3x. That's e to the x minus e to the 3x. This guy and this guy. 1 apple minus 2 apples is negative 1 apple. Now I can factor an e to the x in the numerator. And what will be left is 1 minus e to the 2x. Downstairs, still 1 plus e to the 2x all squared. Okay, everybody with me on this second derivative calculation? I know this was a little bit of work and a lot of algebra. we want to ask, where is f double primed equal to 0? And where is f double primed undefined? F double primed would be equal to 0 if that top is equal to 0. And that top is made up of two factors, e to the x and 1 minus e to the 2x. So I set each of those equal to 0. Of course, this never happens. E to the x is itself never 0. But the other guy, here we will get something. If I add e to the 2x to both sides, this says 1 equals e to the 2x. If I take the natural log on both sides, I get the natural log of 1 is equal to the natural log of e to the 2x, which is just 2x. The natural log of 1 is 0. And then dividing both sides by 2, you get x equals 0 here. Okay, so there is something that happened. Fine. F double prime would be undefined if that bottom is equal to 0. But we know this doesn't happen, right? This would be the same as saying 1 plus e to the 2x equals 0. And we just showed in our first derivative work that that never happens. So there will be something on the number line for f double primed, just 0. So we can proudly plop him right there. Of course, that splits this into two regions. To the left of 0, we can go ahead and plug something negative in. So we could test x equals -1, for example. F double primed of -1 is e to the -1, 1 minus e to the -2 over 1 plus e to the -2 all squared. And I just want to know whether this is positive or negative. E to the -1 is positive. It's 1 over e. It's like 1/3. 1 minus e to the -2 is positive because e to the -2 is like 1/8, right around there between 1/8 and 1/9. And 1 minus something smaller than 1 will be positive. So I'll just write the signs here. This is positive times positive. And downstairs here, this is also positive. 1 plus e to the -2. Well, e to the -2 is already positive. When you add 1 to that, it's going to be positive. So every factor here is positive, which means the whole thing is positive. So f double primed, positive to the left of 0, concave up. If we test x equals 1 to the right, f double primed of 1 is going to be e times 1 minus e squared divided by 1 plus e squared all squared. E is certainly positive. 1 minus e squared, though, that's negative. E squared is like, it's like 2.7 squared. It's between 8 and 9. And so if you take 1 and you subtract like 9-ish, you're going to get something negative. Downstairs, 1 plus e squared is positive. So it's the square of something positive. That's definitely positive. So overall here, we are negative, right? Positive times negative, all divided by positive, that's going to be negative. So we're concave up to the left of 0, concave down to the right of 0, increasing everywhere, positive everywhere. Before we start trying to sketch, we want to think about symmetries and asymptotes. There are no symmetries. What's our original function here? So we're looking at the inverse tangent of e to the x. In order for this to have any symmetries, the inner function would have to have some sort of symmetry, and e to the x we know is not, and is neither even nor odd. So even though the inverse tangent is an odd function, because the inner function here is neither even nor odd, the whole thing is neither even nor odd. We can ask about vertical asymptotes. Well, a vertical asymptote requires that the function is undefined at some value. E to the x, his domain is all real numbers. Inverse tangent, his domain is all real numbers. So you're taking two functions that are continuous everywhere and asking, can it have a vertical asymptote? No. Not. Horizontal asymptotes. Now there's a fun question. Who remembers how to check for horizontal asymptotes? What's the procedure?
Isn't it like factors that cancel out top and bottom or something like that?
There is something like that for rational functions, where you look at the degree of the top and the degree of the bottom and take the ratio of lead coefficients if those degrees match. Canceling factors top to bottom, that creates a hole. But horizontal asymptotes for functions like this, where we're not looking at a rational function, right? The inverse tangent of e to the x, that's like inverse trig and exponential, so no polynomial stuff here. We have to do it the standard way, which is to take the limit as x goes to positive infinity and as x goes to negative infinity. So this is how you look for horizontal asymptotes. You take the limit as x goes to negative infinity and the limit as x goes to positive infinity. If you get some numbers out of that, then those are the horizontal asymptotes. If you don't, then at the very least, it'll tell you the end behavior. Like, is the function going up? Is it going down? So as x goes to negative infinity, that means we're looking lim x to negative infinity, inverse tangent of e to the x. This would be the inverse tangent of e to the negative infinity. What is e to the negative infinity?
Zero.
Very good. Very good. So this is the inverse tangent of 0. And that is 0. So on the left, as x goes to negative infinity, we will have the horizontal asymptote y equals 0. Wait, I'll say this stuff over here. Y equals 0, and this is on the left. What about as x goes to positive infinity? Well, now we're looking at lim x to infinity, inverse tangent of e to the x. And this is one of those special limits that we played with in the past. As x goes to infinity, e to the x goes to infinity. So you could say that this is the inverse tangent of positive infinity. What is that? What does arctan do as its inside gets really big?
It approaches pi over 2.
Excellent. Yeah. So that means we also have a horizontal asymptote that we approach on the right. So this is pi over 2. So the other horizontal asymptote is y equals pi over 2, and we approach that as we go off to the right. Okay. We now have everything you could possibly want to sketch a nice graph of this function. So let's do it. Okay. We're going to make our number line for the shape of f. I'm going to set these papers off to the side so we can refer back to our previous number lines. Not too much to do here. The only number that showed up on any of those number lines was 0. And that was on the number line for f double primed. So here's that. And here are the other two. So both f and f primed were always positive. Since f primed is positive, that means we're increasing always. F double primed is positive to the left of 0. So we are concave up here, and negative to the right of 0. So we are concave down here. So everywhere to the left of 0, we are increasing concave up. That looks like this. Everywhere to the right of 0, we are increasing concave down. That looks like this. And because the concavity changes at 0, that means this is an inflection point. The x value at that inflection point is 0, of course. And the y value there is going to be f of 0. So f of 0, if you plug 0 into the original function f, and I'll do it over here, f of 0 is the inverse tangent of e to the 0, which is the inverse tangent of 1, which is pi over 4. So the inflection point there is at 0, comma, pi over 4. All right, we're ready to draw our graph. I know my function is always positive, so I'm not going to show the y-axis extending down very far. I'll just do it like this. I have the horizontal asymptote y equals 0 that we approach on the left. Y equals 0. I'm sorry, I think this is the insurance company calling me again. Okay, not insurance people. That was actually a student calling. So, hey, that's nice. Where were we? So horizontal asymptote y equals 0 that we approach on the left. We also had a horizontal asymptote pi over 2 that we approach on the right. So we'll sketch in our asymptotes. The only point of interest here was at 0, comma pi over 4. Pi over 4 is exactly half of pi over 2, and that was an inflection point. We know the function is always positive, so he has to approach this asymptote like that. Can't approach it from below, because that would mean the function is negative, and it's never negative, so it's got to be up here. we don't have any maxima, so it can't come up here and turn around. That means we got to approach this from below. And then we just fill in with the shape of our graph. So we know we're increasing concave up everywhere over here. That's got to be something like this. And we know that we're increasing concave down everywhere over here, that inflection point, changing the concavity. And there she is. You can extend this asymptote out on either side if you want. Same with this one if you want. But that is your graph. And the ordered pair here at this inflection point is 0, pi/4. That's it. Not too bad. Not too bad. Is it fast? No. But are any one of those steps that bad? I argue also no. Maybe the algebra with the second derivative. But I hand it to you. What about this, if we were on the exam, would you be nervous about? What would you like to look at more carefully here?
Can you go back to the first derivative and explain it again?
Sure. So for anybody who's still sketching the graph there, I'll do it like this. Here's our first derivative work. So we're starting with the inverse tangent of e to the x. Let me annotate in a different color here. So
And so you immediately rewrote tangent in terms of e.
So our function is inverse tangent arctan of e to the x, right? So f of x and inverse of e to the x. And so in this step, I'm taking the derivative, and I know what that derivative looks like, but we can see where that derivatives come from by thinking about how the inverse tangent function differentiates. Remember when we learned implicit differentiation, that was when we discovered how to differentiate the inverse trig functions. It was a little bit nasty to cook up. We don't want to have to go through that whole procedure. So just like we memorized the derivatives of sine and cosine, we should remember the derivatives of inverse sine, inverse tangent. The way this worked out is that we get 1 over 1 plus u squared if we were differentiating with respect to u. And then if u is a function of x, then we need the chain rule. We have to multiply by the derivative of the inside. So it's 1 over 1 plus the inside squared times the derivative of the inside. So here we had the inverse tangent of e to the x. So that's 1 over 1 plus the inside, e to the x squared. And then by the chain rule, we multiply by the derivative of the inside. And then passing from here to here, I say, okay, well, I know the derivative of e to the x is e to the x. And I know that e to the x all squared is e to the 2x. Because when you raise powers to powers, the powers multiply. So this is 1 over 1 plus e to the 2x times e to the x. And that e to the x is like e to the x over 1. So those fractions multiply straight across, and that gives us this.
Thank you.
Of course, of course. And then the rest of the work from here was a little silly, right? The top e to the x never going to be 0. The bottom 1 plus e to the 2x. Well, e to the 2x is always positive, so 1 plus that is always positive. Or you can just go through the algebra and you see, oh, natural log -1. Okay, that doesn't happen. What else would we like to look at more carefully here? Are we all comfy with how we got the shape? So we're increasing everywhere because f prime was always positive. Concave up over here because f double prime was positive there. Concave down over here because f double prime was negative there. And the asymptote work, that was kind of interesting too, right? We had to be a little bit careful about our limits. Okay. If there are no other questions on this, and really if you have them, this is a good time. If there aren't, then we will move on. Anything else we want to ask about?
So basically with f prime, you basically get, you understand whether the graph is increasing, and then when you take f double prime, it tells you the shape of the graph.
Almost. F prime tells you increasing or decreasing. F double prime tells you concave up or concave down. And then those two things together give you the shape. So we have those four fundamental graph shapes, like increasing concave down, increasing concave up, decreasing concave down, and decreasing concave up. So this is increasing concave up, increasing concave down, decreasing concave down, decreasing concave up. So we need both the first and second derivative information to get the graph shape. That's why we have to build those two number lines before we can do the shape. But yeah, yep, that's the vibe.
Thanks.
Of course, of course. All right, what else? Again, pretend this is the test. Where would you be stuck, or where would we be in trouble? What would we want if this was the test that we don't feel comfortable with yet? Okay, let's take a look at Desmos and see how we did. I'm hoping this is good, but you never know. Good to check. Bam, not too shabby. I'll take it. We can check our asymptotes. There she is. And y equals 0 is pretty easy to see. There we go. All right, not bad at all. Curves like this, by the way, are kind of special. They're often, this is very similar to what's called a logistics curve, where something goes from 0 and rises in a nice smooth way up to some fixed value. You can scale this up by multiplying by some number to make this second horizontal asymptote, make this height whatever you want. Another function whose graph looks similar to that is the one right after this, number 43. And I think you have this or some variation on this in your homework. This is literally a logistics curve, and they are very, very important in statistics and modeling. All right. I think that's enough curve sketching. Oblique asymptotes we do not cover here at Santa Fe, but you find those by doing long division if you want. But what I want to do now is bring us back to the mean value theorem. Mean value theorem, often called MVT, has a nice intuitive understanding that says if you give me a secant line for a smooth function, then somewhere on the interval between the 2 points that make up that secant line is a parallel tangent line. And generally the way this is proved is by first proving the weaker version here called Rolle's theorem. So this is going to start off quite heavy in theory, but I promise we will connect it back to something very concrete. You've got to be patient with me. So this is the section on the mean value theorem. And what's that? Is it 4.2 or 4.3? It's 4.2. I'm sorry. I called it 4.3 earlier. Applications in the Calc 1 level are pretty thin, but if you ever take the class called Advanced Calculus or Real Analysis, you'll see that this theorem is one of the heavy-hitting tools for proving bigger theorems. In fact, a lot of a lot of basic results about the derivative in an analysis class would be proved by appealing first to the mean value theorem. So let's try to build up to it. We begin with Rolle's theorem, which says if f is a function continuous on the closed bounded interval a to b, I should say comma, differentiable on the open interval a to b, and satisfying f of a equals f of b, then something is true. And before I draw or write the something, I want to draw a partial picture here and see if I can get you to anticipate the answer. Okay, so here I have some coordinate axes, and I've just labeled numbers on the x-axis as a and b. I'm thinking about the graph of some function living in here. And let me go ahead and say that the f of a is this y value. And one of the hypotheses of the theorems is that f of a is equal to f of b. That means that this is at the same height. Now, imagine you try to connect these 2 points with a smooth curve in any possible way. What can you tell me about the derivative? Think about all the possible ways you could connect these 2 points. All of those graphs have something in common.
They pass through 0, right?
Almost. Something will pass through 0, but not the graph of f. So if f of a was down here and f of b was up here, then we would have to cross over the x-axis, meaning f would be 0 at some point. But no matter how you try to avoid it, there must be a horizontal tangent line somewhere in there. At least one. There could be several, but no matter how you try to avoid it, if this curve is going to be smooth, right, differentiable everywhere in here, and connected, continuous everywhere in here, then there must be at least one value of c where the tangent is horizontal. And the fun game to ask yourself is, how can I fuck this up? If I relax the requirement that f be differentiable, is the theorem still true? So let's see, can I draw a curve that is continuous, but not differentiable, connecting those 2 points without a horizontal tangent? Can anybody imagine what such a curve might look like?
A V.
Very good. Yeah, a like V-shaped thing. Anything that is kind of pointy would do the job. So this satisfies Rolle's theorem. This does not satisfy Rolle's theorem, right? The hypotheses are not true. And as a consequence, the conclusion is not true, right? Nowhere in here is there a horizontal tangent on this graph. So the picture, the graph of F, it is continuous on the closed bounded interval a, b, and differentiable, which I'm just abbreviating as diffbul here because it takes a while to write, on the open interval a, b. And the point of the theorem is that if these two things are true and f of a equals f of b, then there must be a horizontal tangent line, at least one, somewhere between a and b. Here, f is g is continuous on the closed interval a, b, but not differentiable. In other words, the hypotheses of Rolle's theorem, everything that comes between the words if and then are called hypotheses. Everything that comes after the word then is called the conclusion. So the hypotheses, it says if f is continuous on AB and differentiable on open AB, satisfying this. So the second function here, g, it is continuous on AB, and it does satisfy g of a equals g of b, but it's not differentiable. So if you relax the differentiability, the conclusion need not be true. It certainly could still be true, right? It is possible that maybe I draw a function that's got one pointy bit, but then also has like a curvy min or a curvy max. But the idea is if you relax the requirement that f be differentiable, the theorem might not hold up. The conclusion might not be true. And if you let me break continuity, I can do this lots of ways. There are lots and lots and lots of functions that are discontinuous and don't have anything like that. So maybe one last picture here. So if I'm allowed to be discontinuous, there's a bunch of ways for me to connect these dots without a horizontal tangent. One option is to throw a vertical asymptote in there. So here that discontinuity is enough to get rid of the HTL. H is not continuous on AB. And there are many, many variations on this. Okay, so Rolle's theorem is nice. The mean value theorem is just a slightly enhanced version of Rolle's theorem where the heights at the end don't have to be the same. And then instead of getting a horizontal tangent, you'll just get a parallel tangent. Parallel to what? Parallel to the secant line. So here we go, MVT. Rolle's theorem is a special case of MVT. MVT actually includes Rolle's theorem in it. But the reason we discuss Rolle's theorem first is because to prove MVT, usually you use Rolle's theorem. Proving MVT out of the gate is kind of tough. So this is the mean value theorem, aka MVT. What this says is same hypotheses if f is a function, almost the same, I should say, a function continuous on the closed interval a, b, and differentiable on the open interval AB, then, so you notice there's no and f of A equals f of B, then f primed of C is equal to not 0, but f of B minus f of A over B minus A for some number C between A and B. And the trick to understanding this is to interpret the right-hand side of this equation as a tangent, as a secant slope. Of course, f prime of C is a tangent slope. So they're saying if you have a smooth function on a closed bounded interval AB, then there will be at least one point between A and B where the tangent line is parallel to the secant line. I'm sweating like a pig, so I'm going to turn on the AC real quick. Let's get how it's all in the background. Okay. So what's the picture here? Same sort of setup. Only now f of A and f of B don't have to be at the same height. And the idea is if I connect these 2 points with a smooth curve, no matter how I do it, somewhere in here will be a tangent line parallel to the secant line. You have to remember what the secant line is. Secant line for a function on some interval or between two x values is just the line that connects the dots, the straight line connecting the dots. So that's your secant. And when we say that this expression is equal to this, well, this expression, it's not the equation of the secant line, it's just the slope of the secant line. F of B minus f of A, that's the rise, right? F of B is the y value up here. F of A is the y value down here. So the rise is the top, f of B minus f of A, and the run is B minus A. So this is the slope of this blue dotted secant line. Can you see where the parallel tangent lines would be? I think I see one right around here. And I think I see another one right around here. So what this theorem does is it guarantees the existence of these points on the graph, call them C1 and C2, where the tangent line is parallel to the secant line. Pretty cool stuff, right? So there could be one such point, there could be 2 or 3 or 4. The theorem promises that there is at least one. You might ask, what sort of stuff can we do with this? Well, I have a fun word problem for you. If you think about your graph F as being the position, So position of an object moving in a straight line. Then the tangent lines are instantaneous velocities. Those slopes are instantaneous velocities. And the secant line is the average velocity. So let's say it like this. I leave Gainesville at 9 o'clock in the morning. And an angry cop, angry policeman, takes note of when I get on the freeway. His being angry will be important. This policeman doesn't like me for some reason. An hour later, the cop's buddy sees me arrive in Orlando, which is about 100 miles away. When I get home, the cop writes me a ticket. For going 100 miles per hour on the freeway. Explain. Okay. So what happened? Well, this cop knows some calculus, and he really wanted to write me a ticket. So he knows that I traveled 100 miles in 1 hour. Now, when he saw me, I wasn't speeding. Maybe I was doing 20 or 30 miles an hour. I was just getting on the interstate. And when he saw me coming back, same shit, I wasn't speeding. But if your position function, right, so i.e. My distance from home, t hours after leaving, we can say a few things about this, right? Let's call this R of t. Then the cop knows a few things. He knows that R of 0 is 0. 0 hours after I leave, I haven't left yet. So my distance is 0. And that R of 1, because his buddy in Orlando called him up when I got there, is 100. 1 hour after I left, I was 100 miles from home. So here's my t-axis. Here's the graph y equals r of t. And here's the height 100. In order to issue me a ticket, the cop would need to prove that at some time along the trip, my actual speed was 100 miles an hour. All he really knows is that this point is on the graph and that this point is on the graph. But according to the mean value theorem, if you connect these points with any smooth curve, there will be at least one point where the tangent line is parallel to the secant line. So the secant line here has slope 100. R of 1 minus R of 0 over 1 minus 0 is 100 minus 0 over 1 minus 0, which is 100. So no matter how I was driving, maybe I came in here like this, and then, going slow at first, and then I speed up, and then I get into Orlando like this. He knows that at least one point in there, I must have had a tangent line parallel to that secant line. So this guy right here would be the time when I was going 100 miles per hour. So this policeman can go ahead and write me that ticket as long as he knows two things: that my position is a continuous function of time. That is true. I cannot disappear from one place and reappear in another place. He would also need to know that my position is a differentiable function of time. And if this were to ever happen, not that it would, but if this were to ever happen, I may take the ticket to court and try to argue that my position is not necessarily a differentiable function of time. I am capable of changing direction rapidly, not in a non-smooth fashion. But that's neither here nor there. So the cute point of this problem is that by applying the mean value theorem to the position function, even knowing only 2 points on that graph, only having that tiny little bit of data, how far I went and how long I spent getting there, he can say with 100% mathematical certainty that there was at least one time where my actual instantaneous velocity was the same as my average velocity. So you can go ahead and write me that ticket. This is the classic one. I think it's always kind of cute and it's fun to share. There are other problems that are a little bit more testable, things that kind of feel a little bit more like classical exercises, but I wanted to show you this first because it's fun. Okay. Classical exercises are, here's a function, here's an interval, find C. So let's do them. All right. Let's do number 16. Find the number C guaranteed to exist by MVT for the function f of x equals e to the negative x on the closed bounded interval 0 to 2. First things first, is this function continuous on the interval 0 to 2? If not, then I can't apply MVT. Well, exponentials we know are continuous everywhere. Yeah, this is one of the things that we talked about way back in section 2.6, sorry, 2.5. And similarly, exponentials are differentiable. There's not much to show here. It's just one of the theorems that we have. So we can apply MVT. MVT's hypotheses are satisfied. Okay, well then what MVT says, so for some C, between A equals 0 and B equals 2, right? The interval is the interval A, B, so this is A, that's B. We must have f primed of C is equal to f of b minus f of a over b minus a. So what is that? Well, f primed of x is e to the negative x times negative 1. So f primed of c would be negative e to the negative c. F of b, well, b is 2, so that's e to the negative 2 minus, right, just regular f here, not f primed, minus f of a, that's e to the negative 0 divided by 2 minus 0. So we get negative e to the negative c equals e to the negative 2 minus e to the negative 0 over 2 minus 0. Let's fiddle with this a bit. My goal is to solve for c. So I have negative e to the negative c equals e to the negative 2 minus e to the negative 0 is e to the 0, that's 1, over 2 minus 0, that's 2. Again, my goal is to solve for c. If I can multiply both sides by negative 1, get rid of the negative, that's e to the negative c equals negative e to the negative 2 minus 1 over 2. I'm going to do two things in this step. Well, maybe just one thing. So this is e to the negative c equals, if I distribute the negative over here, this will become 1 minus e to the negative 2 over 2. Now, if I take the natural log on both sides, I'll have natural log of e to the negative c on the left equals natural log of 1 minus e to the negative 2 all over 2 on the right. The natural log of e to some shit is always just that shit. So this is c equals ln 1 minus e to the negative 2 over 2. And then finally, get rid of that negative. C is the negative natural log of 1 minus e to the negative 2 over 2. And that's it. Classic MVT problem. Here's a function, continuous and differentiable on some interval. Great, find me the value of c. And you just take that equation from MVT, the f primed of c equals f of b minus f of a over b minus a, and plug everything in. Then solve for c. We have just a little over 1 minute left. And in that time, I want to show you one other flavor of problem that I think is a bit more exciting because it's not as computational. And I did put one of these in your homework. All right, let's try this. So if f of 1 is equal to 10, f primed is at least equal to 2. How large can f of 4 be? Suppose f of 1 equals 10 and f primed of x is greater than or equal to 2, x 1 less than or equal to x less than or equal to 4. How small can f of 4 be? The idea here is that we're going to apply the mean value theorem to the function f on the interval 1 to 4. MVT would say that f primed of C is equal to f of 4 minus f of 1 over 4 minus 1. Some of these things I know, some of them I do not. I have a little bit of information about f primed of C because f primed of C is the derivative of f, it's f prime. So I know that that's at least 2, but for now, I'll just leave that as that. Just leave it as f prime of C. I know that f of 1 is 10. And I know that 4 minus 1 is 3. Let's isolate f of 4. So I get 3 times f primed of C is f of 4 minus 10. And that means 3 times f primed of C plus 10 is equal to f of 4. So there is some number C between 1 and 4 such that this is true. They asked me, what's the smallest possible value for f of 4? And I know that this number, whatever it is, has to be at least equal to 2, greater than or equal to 2. So if since f primed is greater than or equal to 2 on 1, 4, we know f primed of C in particular is greater than or equal to 2. So then 3 times 2 plus 10 is the smallest possible value of the left-hand side. I'll say it like this. Since f prime is greater than 2. The smallest possible value of 3 f primed of C plus 10 is 3 times 2 plus 10, because f primed is guaranteed to be at least 2. So this is less than or equal to f of 4. F of 4 could be bigger, but it can't be smaller, because f primed is going to be at least equal to 2. Could be bigger, can't be smaller. Now 3 times 2 plus 10 is 16. So f of 4, 16 is less than or equal to f of 4. In other words, f of 4 has to be at least as big as 16. F of 4 can be no smaller than 16. I really like these problems because it always feels surprising to me how much you can get out of MVT with a shockingly small amount of information. Think of the COP problem, same sort of thing. With a shockingly small amount of information, you can learn a great deal about the function f. And just a tiny smidge of information about the derivative. That's all you need. So this is where I'm going to wrap up for you guys today. If you submitted an extension request over the last few days, I extended it all the way through to the 14th to the end of spring break. So you have time to work on that stuff. If you need more time on any of the other homework sets, or you anticipate needing more time, please go ahead and put in an extension request. And again, I'll push that to the 14th for you. Remember, our exam is going to be the Friday the week we come back. So you have a total of 2 weeks between now and the test. And that might sound like a good thing, but believe me, that is fucking dangerous, because that's time to forget. That's 2 weeks to forget all the shit we've been doing. Don't forget, right? How do you not forget? I talk to anybody who speaks more than one language. You practice, right? If you don't practice it, if you don't use it, you lose it. This is the same way. So I am going to also publish your study guide. And your study guide, you can work on that at whatever pace you want to, but I strongly recommend that at least 2, 3, 4 days over spring break, sometime over that whatever 9-day gap where we're not going to see each other, make sure that on at least 3 or 4 days, you sit down and spend a few hours working some math problems. Don't rush it, don't panic. It's not like that. I just want you to keep up. You know, I don't want you to forget everything between now and the test, because that would be sad. I will be responding to emails over break. I will not be doing the office hours unless you need something. If somebody messaged me and says, please, I need an office hour today, then I'll work with you. But I'm not going to be doing the regular office hours thing. I'm on break too. But I will definitely be responding to emails. So if there's something like that you need from me, please let me know. Work on the study guide. Don't forget. All right. Don't forget all the math we've learned. It's beautiful stuff. I want you all to rock this test. You've got time to study. That's the advantage of the long stretch here. Make sure you use that time to study. If you don't, then it will bite you in the butt. A lot will just drift away if you don't use it. So please work hard on the stuff. If you need anything from me, don't hesitate to ask. Is there anything you guys would like to ask or talk about before I end the meeting here?
For the Monday and Wednesday that we come back, are we gonna be doing like the next lessons, or are we gonna be doing it like a review day?
Wednesday, I will do a mostly review thing. Monday, I think I'm going to introduce where we're going after the test. So there won't be any new material between now and the test. Monday, I'm going to kind of prep you guys for this notion of an antiderivative. And the thing we're going to do after the test, which is related to what's called integral calculus. And then Wednesday will be your day. You can ask whatever homework, quiz, test questions you want. And then Friday will be the test itself.
I thought an antiderivative was an integral.
Yeah, they are.
Okay.
We don't know that yet, but yes.
Yeah, I'm dating a physicist. So.
Cool. Yeah, I am married to a physicist. It's nice. It's nice.
Yeah, so they're very helpful when it comes to calculus stuff. But okay, thank you.
Yeah, of course, of course. All right, anything else, guys, before we wrap up here? Okay, enjoy your breaks. Please be safe. Don't get hurt. People are fucking crazy out there. That lady hit my car this morning. I'm sure there's gonna be a lot more of that crap over the next week. Watch your ass, stay safe, have fun, relax, and remember to do a little bit of math every day. Take care.